Namaskar and welcome to BioAffairs. So today I'm back with Radioimmunoassay. Before that I've already finished direct, indirect and competitive ELISA. So Radioimmunoassay is a type of competitive ELISA. It is availing the principle of competition, but it is different from competitive ELISA. So let's know how it is different and how you can detect an antigen through this radioimmunoassay. So this radioimmunoassay can be used for the detection of antigen or antibody. For qualitative and quantitative, means you can only detect the antigen or you can quantify the concentration of the particular antigen in your sample or in the patient sample. So I will show you first how to detect the antigen, then I will tell you how to quantify the antigen in the patient serum. So let's start. So radioimmunoassay, you need three things mainly. Patient serum, that is the unlabeled antigen. It is the natural antigen. Then you need a radioactively labeled antigen. So radioactively labeled antigen is used for or used against the unlabeled antigen, which is the original antigen. And the competition will be within these two antigens. I will tell you. So here the radioactive material used is iodine 125 or tritium H3. Most commonly iodine 125 is used. So I have given different colors so that you can understand my images clearly and the concept. So unlabeled antigen is in blue, radioactively labeled antigen is in red, and of course you need a monoclonal antibody or the antibody which is designed to recognize both radioactively labeled antigen and the unlabeled antigen. So this is the preliminary three things you need. Then of course you need a microtiter well plate which is made up of polystyrene or polyvinyl. Now let's take an example of a well. So this is a well. So this well is previously coated with antibody. So monoclonal antibody is captured here in this well. So it is a coated well. Now in this coated well, you can see the first step I have given labeled antigen. That means radioactively labeled antigens. So there is no competition. Antibody binding sites are free. So all the labeled antigens will bind to the available antibodies. Okay. So now we have the bound labeled antigens. Now you have to incubate for some time for the attachment time and then wash. So I am writing this as incubate and wash. I and W. I for incubate, W for wash. Now in the next step, you will be adding the step 2 unlabeled antigen. Unlabeled antigen now will compete with the radioactively labeled antigen for what? For the fragment of antigen binding sites. The sites. So gradually it will replace the radioactively labeled antigens with the unlabeled antigens, because naturally the original antigen against which the monoclonal antibody is developed has a higher affinity and ability towards the natural antigen. So the concentration is also a factor, I will say, but the mechanism is naturally unlabeled antigen will replace the radioactively labeled antigen that I have drawn in the next week. You can see here that here 4 antigens are bound, radioactively labeled, but when I added unlabeled antigen and then incubated for some time and washed off, incubated and washed, then you can see here only 3 only one labeled antigen is there and 3 unlabeled antigen or the serum antigen is present in the bound condition, and these are the unbound free labeled antigens. So after that, what will happen? I will incubate, wash, and will measure the radioactivity in gamma counter. So how we have detected the patient is positive or negative? As you can see previously, the radioactivity, if you measure this well, the first well, means the first step, after adding the first step, there will be high amount of radioactivity will be captured by the gamma counter. But if the patient is positive for the antigen, there will be much reduction in the radioactivity percentage, and that will be reflected in the gamma counter. So if a negative patient is there, then all will be bound to the, or most of the antibody binding sites will be radioactivity labeled antigens. So the radioactivity percentage will be much more higher in case of negative patient. But in case of positive patient, the radioactivity is much more lesser, which will give you a qualitative detection of the patient, that the patient is either positive or negative. So this is the mechanism for detection of the patient with the help of percentage of radioactivity shown by the particular wells or the experimental wells. Now let's consider you want to know the concentration of the serum antigen present. Okay, so I will draw and will explain you. To measure the concentration of the antigen, you have to take a microtiter well plates. Of course, all the experiments are going on in the microtiter well plates. I am trying to say here, you have to take a row of the, or number of wells in a row to form the standard curve. Without a standard curve, we will not be able to estimate the actual concentration of the serum antigen. So suppose I have drawn here 4 wells. So suppose this is the first row of a microtiter well plate. In the first row I have taken 4 wells. Okay. Now in that 4 wells, the same wells which are antibody coated wells, same as I have drawn previously in the previous image. Now what I have given? I have given labeled antigens. Radioactively labeled antigens given to all the wells. Okay, so what will happen? All the antibody binding sites will be occupied by the radio labeled antigens, right? So after incubation, after a few minutes, I will wash it off. So now I have all the radioactively labeled antigens where none of the unlabeled antigen is present. Okay. Now this is the first step. Now I am going to the second step where you will be adding known concentration of unlabeled antigens. Remember that, known concentration of unlabeled antigens. This is not the serum antigen. Okay, known concentration, it will, you have it in the kit provided that you know that 10 microliter of the serum contains 1 nanogram of the antigen. 20 microliter will contain 2 nanogram of antigens. Likewise, company has given you known concentration antigens. Okay. Now this is the same antigen present in the serum, but this is estimated and known concentration of the antigen that is provided to you by the company. So now suppose I have left the first well. So here none of the antigen is given. So suppose 0 nanogram of original antigen or the unlabeled antigen. Okay. Here I have given 1 nanogram of unlabeled antigen. Here 2 nanogram of unlabeled antigen. Here 4 nanogram of unlabeled antigens I have given. Now see the changes. As I have given 1 nanogram of antigen, some of the radioactively labeled antigens are replaced by the unlabeled antigens. Here see, you can see if you consider this 0 nanogram, 6 antigens are bound. Here 3 are bound with the help of only 1 nanogram of unlabeled antigen. Here 4 are bound and 4 left the place radio-labeled and 4 unlabeled antigens bound to the antibody. Here 5 of the unlabeled antigens bound to the antibody, only 1 left with 4 nanogram concentration unlabeled antigens. So this is the standard you have to prepare, standard curve you have to prepare to know the concentration of the antigens. Now let's draw a curve. So when you have 0 nanogram of unlabeled antigens, the radioactivity, suppose the radioactivity was 100%. Now when you have added 1 nanogram of unlabeled antigens, the radioactivity is 80%. Now when you have 2 nanogram of unlabeled antigens, radioactivity reduced to 60%. And here you say 40% reduction of radioactivity, because the radioactive components or the antigen is leaving due to the addition of unlabeled antigens at different concentration. Here I have drawn in increasing concentrations. So that why likewise I will draw here. So 0 nanogram, then 1 nanogram, then 2 nanogram, then 4 nanogram. So for 0 nanogram, it is 100. Let's mark it 100, 80, 60, 40, 20, 10. Now, when you have added 1 nanogram, it is 80%, right? When you have added 2 nanogram, it is 60%. When you have added 4 nanogram, it is 40%. So if you draw a line, what will happen? This is the standard curve line. Okay. So now we have the estimation. This is the nanogram per microliter or per ml, you can say, per ml of known unlabeled antigens, and this is the percent radioactivity. X-axis is the concentration of the antigen, and the y-axis is the percentage of radioactivity. Now you have this curve. Now suppose go to the experimental plates or experimental wells where you don't know the concentration of the serum antigen. You do not know that patient 1 or patient A has how much concentration of the antigen, patient B has how much concentration of the antigen, you don't know. So let's consider patient A. So I have drawn that graph in a larger way so that you can understand. Previous picture was too much cozy. So here the same graph, the x-axis showed the concentration of the antigen which I have received from the previous image, and the y-axis is percentage of radioactivity shown by the wells. So I have taken 4 wells, right? In that 4 wells I have given, in the first well, 0 nanogram of unlabeled antigen, unlabeled. This unlabeled antigen and this unlabeled antigen is different. This unlabeled antigen is given in the kit. Our company will provide you this unlabeled antigen, okay? Because it is known concentration. Known concentrations of unlabeled antigens are provided to you other than the patient's serum antigen. So don't confuse with this unlabeled antigen. This unlabeled antigen is only provided to you for preparing the or for synthesizing the standard carb. This is a standard carb, because without this carb you will not be able to know or find the concentration of the actual antigen present in the patient serum. So I hope I am clear. Now, as I have shown that 0 concentration, 0 nanogram per ml of antigen, unlabeled antigen, replaces none of the radioactively labeled antigen. That's why the radioactivity shown was 100%. In the second well, 1 nanogram is given, radioactivity reduced to 80% because some of the radioactive antigens left the fragment for antigen binding sites, and that site is occupied by this unlabeled antigen. Again, I have increased the concentration to 2 nanograms. So this gives you 60% of the radioactivity. Radioactivity again reduced because some of the radioactively labeled antigen was lit off. Okay, there is every step there is an incubation and wash. Don't forget that. I don't need to say you again and again that every step, every addition of reagent, you have to give some time. That is called incubation time for attachment, and then you have to wash it off to release all the, or to not to release but to remove the unbound antigens or antibodies. This is the most common process in all the ELISAs. Okay. So likewise, in the 4 nanogram concentration, it gives you 40% of radioactivity. So as you have increased the number, or so not number, the concentration of the unlabeled antigen, the percentage of radioactivity proportionately reduced. This gives you a standard carb. Now this standard carb will be used to find the patient is serum. This is the patient serum antigen concentration. Now see how. So in the experimental wells, this is experimental well where you are giving actual serum, patient serum antigen. So first the process will be totally same. First it is antibody coated well. You have given the radio labeled antigen. It is all bound. It is all set. Now incubated and washed. So all the radioactivity labeled antigens are washed off, which are unbound. Then you have added patient serum, which contains the antigen, right? So it will compete with the binding sites for the radioactively labeled antigens with the antibody. So you can see here 4 molecules of radioactively labeled antigens were there, and after addition of the patient serum, only 1 is left, 3 is there. So you can see here, if it has showed you, if it showed you 100% radioactivity, this will be reduced to suppose 40%. Suppose, okay. So now this serum antigen, whatever amount you have given, 10 microliter, 5 microliter or 2 microliter, that can be found easily, no issues are there. But that serum antigen, which corresponds to 40% of the radioactivity, will be put in here. So 40% means your antigen, your patient serum antigen showed 40%. So this dot. So if you just draw a line here, so the actual patient contains 4 nanogram of the concentration of the antigen. So the serum contains 4 nanogram per ml of antigens. So likewise, you can find as many as patients, okay, but you have to find this curve first. Then you have to measure the radioactivity for the experimental wells. So I hope I am clear. If you have any doubt, please ask me in the comment section, or you can mail me also. Okay, thank you very much. If my classes are really helping you in your studies and it is really clearing your concept And if you really like my classes, give a big thumbs up and don't forget to subscribe my channel BioAffairs. This type of subscription and likes give me the enthusiasm to prepare more futuristic classes for you guys.